Hello and welcome back to Physical Geology. I am Robert Lopez, and today I actually want to talk about Chapter 13 in your textbook, which deals with unstable ground and this idea of mass movement, which I normally call mass wasting, but your book goes right ahead and says mass movement is mass wasting, which is essentially the downslope motion of material. It could be rock, this material called regolith, and regolith is basically the soil, loose sediment, or any debris that's not really part of the bedrock. And also other types of mass movement or mass wasting include snow avalanches or chunks of glacial ice breaking off and coming down the slope. So really anything that's moving down slope. Again, mass wasting is mass movement. We talked about regolith a little bit. So it is a natural hazard just like earthquakes and volcanic eruptions, right? Geologists distinguish among many different kinds of mass wasting, and we really look at four features. We look at what's being moved. The second thing we look at is how fast is it moving. Is it going slow? Slow in terms of centimeters per year or millimeters per year, pretty slow in some cases. Some cases they can go maybe 10 to 20 feet per year, 30 feet per year, intermediate, and some can travel very fast, up to 300 kilometers per hour. The character of the moving mass, well, is it coherent? Is it a chaotic mess, including sediment and rock debris, or could it be a slurry, like mud? And then finally, the fourth feature we look at is, well, the environment in which the movement takes place. Obviously, most of the mass movement we're going to be looking at is subaerial, which means under, here on land. Although we will look at some features that are submarine or subaqueous. In fact, I'll show you some landslides or some subaqueous landslides in the Lake Tahoe region. Now, again, we're looking at velocity, slow versus fast. So on this chart, we're looking at slow features like this idea of creep. Creep is a more or less continuous movement of material downslope, and it occurs in a variety of different ways, mostly with freezing and thawing or wetting and drying, so it's going to be kind of a yearly cycle. Another feature that's not shown here is this idea of solifluction, and that has to deal with permafrost, and I'll talk about what happens in permafrost, where the soils basically are going to be slumping off of the frozen material that's several meters down. And then the slumps can mostly are slow, but they can actually have some velocity. They can move several feet per day in some cases. But the key thing about slumps, in fact, most people when they think of a landslide, they think of a slump. That it's going to have some coherent nature. You can see there's some coherent nature. You can kind of make out the debris slumps that are sliding down here. And then now we get more of this chaotic material or slurries of material called lahars or mud flows. And you can see, remember a lahar has to deal with volcanic ash, whereas a mud flow can just be fine-grained material moving at a relatively fast rate. And then we can get debris flows, debris avalanches, rock slides, and rock falls. So all these are moving a little bit faster, a little bit more chaotic, and you can see we're dealing with different types of rock material as well. If it's mostly softer material with very few rocks, we call that debris. But if we can actually make out the rocks coming down, we're going to call that a rock slide. Or if there's a vertical drop, a free fall of rock, then we call it a rock fall. One thing that's not shown on here are the snow avalanches, but those are moving pretty fast as well. Now, this idea of creep, remember this is the slow, gradual downslope movement of regolith. So it's mostly dealing with the regolith movement. And so this idea of freezing and thawing is in the winter, when the ground freezes, it actually expands. But note that the expansion is normal or perpendicular to the slope. So the material will move directly up as freezing occurs in the winter. So we'll have a winter slope. But then the thawing in the spring, the material will remember, the volume will decrease because remember ice has a greater volume than liquid water. And that decrease in volume will cause the grain to move directly down or vertically, right? So we'll get this gradual downslope movement material with the freezing in the winter perpendicular to the slope. Thawing, which is due to gravity, or the pull of gravity comes down. Then again, the next year we see freezing. Then we see thawing in the spring, freeze. So this is happening very slowly over time. This regolith or soil material is moving down slope. In wetter climates where we're having wetting and drying, during the wet season, the pore spaces may expand. You may lose a little bit of cohesion between the grains, and the surface regolith may creep slowly downhill. But then when it dries, the cohesion will increase because the pore spaces or the water in the pore spaces decreases, right? But again, creep is the slowest of these features of this downslope mass movement. Again, how do we detect sleep? We'll see these curved trees. We'll see tilted telephone poles, tilted gravestones, walls that are cracked in the roads, foundations in homes being cracked. I think I have another slide here. Yeah, we're seeing older gravestones more tipped than younger gravestones. Here's our tilted trees, tension on telephone lines, fence posts that are broken up, bent or broken walls, right? Now, this idea of solifluction has to deal with in the spring when there's a thawing. Remember, only the first 1 to 3 meters will thaw, but there's a permanent frozen layer beneath this, right? So the water that will form in this upper 1 to 3 meters has nowhere to go. It cannot penetrate or percolate into the groundwater. So if it cannot percolate, it slides along that frozen permafrost that lies beneath there. So meltwaters cannot penetrate due to this deeper permafrost, and so you get this slumping or sloughing, or really, I'm not sure where this word solifluction comes from, but it describes this movement of regolith in regions of permafrost, obviously colder climates here. Again, the slump, these are going to have the more coherent nature. You'll see a classic headscarp and some other secondary scarps that may occur as well. So these are these sliding slump blocks. There'll always be some failure surface, right? So it's usually spoon-shaped where the mass is curving. And I don't know if you can make this out. There are these kind of depressions and hills and little perturbations in the mass of the landslide, and geologists call this a hummock. And so hummocks, which is spelled H-U-M-M-O-C-K, a hummock or hummocky topography is a classic indication to geologists that there are landslides. In fact, we can sort of see some hummocks developing right in here. These kind of closed depressions where water really doesn't drain away. It kind of internally drains in this landslide or this slump, right? So this would be the hummock debris region, and here's a headscarp. And then we often call this a toe of the slide, almost like these reverse faults being thrust over here and kind of running over themselves. In fact, the author of this textbook, Stephen Marshak, has a good video on a slump, and I'll include this in this lecture series toward the end. Mud flows, debris flows, lahar, so these are mass movements. They're faster when there's more water. Obviously, if there's more water, there's going to be expansion of the soils, which means there's less ability for friction or cohesion, which will allow the material to slide more quickly, right? And also these mud flows will tend to follow existing river channels, right? And then they spread out into this lobe when they reach the base of the slope. They can carry boulders, houses, so some can move quite rapidly and are very dangerous to people. So again, the mud flows is a moving slurry of mud, so it's mostly fine-grained material. Debris flows will include mud and larger pebbles to even boulder-sized particles, so those are debris flows or debris slides. And then finally, these volcanic mud flows we call lahars, are mixtures of volcanic ash, melted snow, or just heavy rains in a volcanic area. And so here's an example of some mud flows in Brazil. I think both of these are from Brazil. And then here's a debris flow where we're seeing some larger rock particles also mixed in with some mud. And then finally the volcanic mud flows. Remember, a rock slide will be mostly rock debris. There could be some other finer grained material, but what you'll find is that the rocks are pretty much always in contact with the slope. It's a steep slope. Obviously, the steeper the slope, the more likeliness of the slide, but the key to a rock slide is that the rocks are never free falling. They're always somehow in contact with the slope. So again, let's say so rock slides, you're seeing mostly rocks or only rocks. Debris slides, you're seeing rocks plus that soil, that finer material. Again, both of these is a non-vertical slope where the rock is in contact with that slope. Now, bedrock or regolith detaches from slope, slips rapidly down on a failure surface, and breaks into a chaotic jumble, right? So these can move quite rapidly, up to 300 kilometers per hour. Momentum may carry debris up opposite side of the valley and on a cushion of air. In fact, a good example of that is, here I have Google Earth showing the Chaos Jumble. So Chaos Crags, these are a series of lava domes near Lassen Peak. This is Lassen Peak in Northern California. The last eruptions here are about 1915, 1916 to about 1921. So these are some of the recent eruptions during that time. But these Chaos Crags, you can see they're also not vegetated. And so they also had an eruption in about 1100 years ago. That's about how old these are. And then based on some of the trees we see here on the rocky rock slide from one of these Chaos Crags, these Chaos Jumbles date back to about 300 years. And what happens is one of these lava domes during an earthquake probably detached, slid down on a cushion of air, and flowed for more than 2 miles, and actually went about 400 feet up the opposite slope here. Right? And here's another picture of it, showing again the Chaos Crags and those Chaos Jumbles. Now remember, for the rock falls, these are free fall from cliff for at least part of their journey. So here are some sandstones where some of these joints are allowing some of these blocks to break off, probably free fall for a short distance, then they'll tumble down this slope here. Remember, this slope where you have all this broken debris is called a talus slope. So actually, I'll post this Yosemite rockfall video as well, so you can take a look at some of the rockfalls that have occurred in Yosemite. I have some other features here. So remember, creep or solid fluxion will be the lowest or slowest, whereas slumps, mud flows, debris flows, rock slides, debris, these are a little bit faster. And the fastest material would be the debris falls, rock falls, and snow avalanche. I may have a question asking, well, the velocity of a slide or a mass wasting event really depends on 3 factors, and those 3 factors include steepness of slope, water content, and air content. Submarine slides. This is actually off of the California coast and off the continental shelf here. So we're looking at the submarine environment. This would be the shallow continental shelf. This would be the steep slope, right? So that's the steep inclination toward the deep part of the ocean. So out here we're looking at about a mile and a half to 2 mile deep water out here. This would be shallow water, only about maybe 600 meters, which is about 1,800 feet or so up here on the shelf. And so you can see that there is a main scarp, and we had a big debris slide, a submarine slide, occurring here off the continental shelf. You can see there's another one that's forming right in here, right? So a little head scarp and debris coming down this way. One of the problems with having these submarine slides, if they're large enough, they can cause a water column above these to move up and down. And if you get the water column moving up and down, they're going to create a wave, a wave with a long period or a long wavelength, and those are called tsunamis. So you can actually get tsunamis that develop from these submarine landslides. So geologists distinguish between 3 different types of these submarine mass movements. Some are submarine slumps, which are more coherent masses. So if we go back to this picture here, this would be more of a submarine slump right in here. We would have submarine debris flows. They break into chaotic material. So that's more like what we're seeing here. We got this kind of chaotic material kind of all over the place in here. And then we'll also see these turbidity currents, which are mostly slurry material. And we've talked about these. These are the ones that make the rocks called turbidites.